Hello, and welcome to Patch Math, where today we are going to talk about trig inverses. But before we do, this video is going to focus in on regular trig functions first, so we can understand how theta and our side lengths interact on the unit circle. Let's get started. So, for the purposes of today's lesson, you will be using the domain and range to check to make sure that what we're inputting into these trig inverses can actually be input. That's super important. And to use the range to help us select the correct output. Now, generally, these are done on the unit circle or with a calculator. There are some other solving methods, but you would be giving additional information for those, so I'm not going to go into them. But if you're given a setup like this, one of two ways: a unit circle or on your calculator. Now, that did not come through clearly. One moment, please. But this one did. All right, so here is our unit circle. If you're at this point in pre-cal, I'm going to assume that you have this memorized or you can recreate it based on understanding. Something else important to make a note of here. We are dealing with thetas. These are angle thetas, these openings. So that would be, if that angle right there, that were a theta, that'd be an angle 30 degrees theta, or that theta equal pi over 6 in radians. So the theta is our angle, and we are going to output a side length. And so, depending on what we're dealing with, x or y will determine cosine or sine. So, x is on our unit circle, r our cosine, super important. X is equal to your cosine of your theta, all right? And y's are equal to your sine. Now, that's kind of opposite our intuition, because usually whenever we learn about sine and cosine, we learn about sine first. And because x is first in ordered pairs, my brain goes, sine must be x. No, it's not. I don't know why my brain tries to make that association. It does. Even as a teacher, sometimes I'll be like, my brain really wants to think that sine is x because we learned sine first. I don't know why. But no. X is cosine of theta and y is sine of theta. Make sure that's understood. So in this situation, if we were looking at like the theta of 30 degrees, right? The cosine of 30 degrees, I'll sketch that out here. So the cosine of 30 degrees, and I actually prefer radians. If you are in pre-cal, you'll know why. We traditionally work in radians, so I'm just going to write that as pi over 6 rather than 30 degrees. They are the same thing. And then if we're trying to find the cosine of pi over 6, well, we just go to that x. That is your cosine. So x is your cosine. In this case, it is going to be square roots of 3 over 2. So that's that length there. All right, you input an angle and output a side length. With that being said, let's go ahead and look at sine. If we were dealing with sine of 30 degrees, it's a little bit different. Our sine of pi over 6, same thing. It's a little bit different because we're looking at a different part of the triangle. So if we go ahead and look, we're making triangles here. These are right triangles. We come up. That is a very not good straight line, but that's a very bad sketch. But see, this is our right angle. And so depending on if you're dealing with your x or your y, you're going to be dealing with base versus height, but they're side lengths. And then we're looking here. So sine of pi over 6. Well, if we take our handy dandy highlighter, that's y. So that's 1. So yes, I did not start with inverses, but I wanted you to have an understanding of what normal trig functions look like on the unit circle, what we're looking at, what x is, what y is, and go from there. There is one more piece of information I need to give you. And that's tangent because it's going to pop up today as well. And I just want you to have awareness of what tangent looks like in its normal form before we get into the inverse. Now, it is a little bit different than sine and cosine. It's actually based off from sine and cosine. So if we're looking at tangent of some theta, of some angle on our unit circle, and we go ahead and we are trying to find that output, that is a ratio of your y's over your x's. So in other words, let's go ahead and translate what this means. Your y is equal to sine of theta. So we can actually write it that way if we wanted to. Recognize that a alternate form of this, is just substituting, if we're going to use the math word for it, substituting that sine, and I'll color code a little bit here, that sine of theta in for your numerator, your y. All right, sine of theta over your cosine of theta. And I did that in gold, so let's pick a gold color here. All right. So bringing that, highlighting your y's, your sine, your x's, your cosine, and that's just its two alternate forms. Now, I prefer to think about it in this form, but if you prefer to think about it in this form, it's the same. Now that we have all that sketched out, what is tangent of 30 degrees? This is super important. So what is tangent of 30 degrees? Well, I'm going to go ahead and write it in the light blue color that we were dealing with there. So this is just like a little example of what tangent looks like on the unit circle. Tangent of 30 degrees, or pi over 6, because I'm dealing with radians. So pi over 6, tangent of pi over 6. Well, that's going to be whatever your sine was. So we could go up here. And the only thing that I don't like about tangent is we usually have a fraction over a fraction. There's different ways you can write this, but I'll show you how I visually divide mine up so that way it makes sense for me. So y's over x's, our y here, well, for 30 degrees, our tangent here, that was 1/2. So that 1/2 gets brought in right here. So our y was 1/2. Our x was square roots of 3 over 2. That's square roots of 3 over 2. Now, pardon my very messy handwriting there. Shrink that down just a little bit. That barely looks like a square root of 3 over 2, doesn't it? All right, move that on down. So notice I really made that middle fraction bar bigger. For me, I'm a very visual person. I like my information divided up. So when we're looking here, the reason I wanted you to think about it this way, when we have a fraction over a fraction, we have this little trick, and I generally don't like tricks, but this one is super helpful. So we can apply what's called keep, change, flip. We keep our first fraction. We will change that division to multiplication. And because we change that division to multiplication, we do have to accommodate for that change by flipping our second fraction. And now suddenly we have two fractions that are being multiplied, not divided. That is so much easier to deal with. And here's my favorite thing about multiplying fractions. You can reduce on a diagonal ahead of time. Now we can multiply straight across the top and multiply straight across the bottom and get 2 over 2 square roots of 3, and that would be great. However, because multiplication and division are created equally in PEMDAS, we can choose to cancel on a diagonal. We can choose to do the division before the multiplication. So we're like, okay. Oh, and we have the commutative property that allows us to switch the 1 and the 2, because if you have 1 times 2, we can write that as 2 times 1. And the same thing with the 2 and square root of 3. If we wanted to apply the commutative property to that multiplication, to 2 times square root of 3, we can also do square root of 3 times 2. So there is a commutative property going on here as well. In my last video, you heard me talk about how those properties pop up everywhere in mathematics, but we talk about them at the beginning of the semester and then really don't talk about when the large portion of them pop up, and it's just interesting. That cancels. So we don't have to reduce at the end, we can reduce at the beginning before we even multiply, and we have 1 over square roots of 3 left. Now, if you had the 2 over 2 square roots of 3, those 2's would just reduce there. This is tangent, all right? Now this, I actually did something that is considered mathematically not good. I'm going to move this on down because of the way we were working here. I needed to write this as a running equals. So let me get this as a running equals. We don't have 2 sides to our equation. We're given one, we're going to find the other. All right, so tangent of square roots, or tangent of pi over 6 is 1 over square roots of 3. These are your 3 most common trig functions that you will see. These are just the examples, what they look like on the unit circle. So now that I spent 10 minutes discussing not the inverses, let's talk about how this translates to inverses. It makes it a little bit quicker.